This is a question about a transformer, okay? If you have one of those little power cubes, the little wall warts, okay, that run portable electronics, it has an output of 4.5 volts and 600 milliamps when it's plugged into a 120 volt outlet. And we were asked about the number of turns on the secondary coil and the peak current in the primary coil. But before we get to calculating that, let's do some preparation. Here's what the situation looks like. We've got a transformer, and it's got a primary that's linked via the iron core to a secondary, and the secondary has a voltage of 4.5 volts, and that's an RMS value, and it's got a current of 600 milliamps. And I'm just going to leave that in milliamps, and we'll see why that doesn't make any difference. The number of turns on the secondary, we don't know. We're asked to compute that. We do know the number of turns on the primary. The number of turns on the primary is 400. Okay? We also know this about the primary. The voltage, RMS, is 120 volts. It's typical household voltage. We don't know the current in the primary. Okay? So this is our basic setup for our transformer. And then we've got some relationships that connect the voltage and the current in the primary and the secondary. And let's start with this one. The voltage in the secondary is equal to the voltage in the primary times the number of turns in the secondary divided by the number of turns in the primary. Okay, that's our basic transformer relationship. Now, the first thing we're going to be asked to compute is this. And let's step into solve mode here. We're looking for the number of turns on the secondary coil. That is N2. Well, we can take this equation and we can rewrite it this way. The number of turns in the secondary coil is equal to the number of turns in the primary coil times the voltage on the secondary divided by the voltage on the primary. And those are all numbers that we know. There's 400 turns on the secondary. The voltage on the secondary is 4.5 volts. The voltage on the primary is 120 volts. And so we compute 15 turns of wire on the secondary. Let's do a quick assessment as we go. We know it's a step-down transformer, and so we expect smaller number of turns on the secondary than on the primary, and so this result makes sense. And since the voltage gets stepped down quite a bit, we'd expect quite a fewer turns on the secondary than the primary. So the assessment, this one looks good. That's our number of turns on the secondary, 15. Now the second part of the problem is this. We're looking for the peak current in the primary. We're looking for I1. Now, rather than use transformer relationships, let's do this. Let's just use the fact that we're going to imagine it's an ideal transformer. And so the product of the current in the primary times the voltage in the primary is going to be equal to the product of the current in the secondary times the voltage in the secondary. So we can compute this. The current in the primary is equal to the current in the secondary times the voltage in the secondary divided by the voltage in the primary. And so what that says is this. If the voltage steps down, the current will step up. So I'm going to have a smaller current in the primary than I have in the secondary. Well, we know all of those numbers. We know I2, we know V2, we know V1. And so what I compute is this. I'm just going to go ahead and put in I2 is 600 milliamps, V2 4.5 volts, V1 120 volts. And so I'm going to compute I1 in milliamps, which is why I didn't worry about the conversion. And what I get is 22.5 milliamps. But remember, this number is an RMS value. Okay, it's an RMS value, but we weren't asked for the RMS value. We were asked for the peak current. To compute the peak current, I'm just going to label it this way. The peak current is just equal to the RMS value times the square root of 2. So it's 22.5 milliamps. But then I multiply by the square root of 2, and so I end up with the peak current of 32 milliamps. Now, let's do a quick assessment of this result. I expect that the current in the primary is less than the current in the secondary. The voltage steps down, the current steps up. So this number seems reasonable. And then the peak current is going to be bigger than that. And so this result seems reasonable. We have a reasonable number of turns, we have a reasonable current in the primary, and so our assessment is that these results match what we would expect. Everything looks good. And this works the way we expect a transformer to.